So the next and final talk of this session will be on impossible boomerang attacks, which is a work by Xavier Bonnetin, Margarita Cordero, Virginie Allemand, Marine Minier, and Maria Naya Plesencia. Virginie is giving the talk.
Thank you for the introduction. So boomerang distinguisher have been introduced in 1999 by David Wagner, and they can be seen as a variant of differential distinguisher. For a differential distinguisher, you will look for two differences, alpha and delta, so that if two messages differ by alpha, then with high probability, their ciphertext difference will be equal to delta. What is meant here by high probability is a probability higher than 2 to the minus n, where n is the block size. Now, for boomerang distinguisher, we will look for four differences, and these four differences will connect together a quartet of messages instead of just a pair of messages. More into details, the relation we will look for is the following one. We start with M1 and M2 that differ by alpha. We obtain C1, C2 at the difference of delta and delta prime. We obtain C3, C4 that will ask for decryption. And here, at this point, we will check that the difference between M3 and M4 is equal to alpha prime. So in most of the attack of the literature, we will choose alpha to be equal to alpha prime and delta that is equal to delta prime. And in this case, we can understand where this naming of boomerang comes from. This is because here we are sending a difference of alpha into the cipher, and we hope that it comes back between M3 and M4. So a few years after that was introduced the impossible variant of these two types of distinguisher. So we have here on the left an impossible differential distinguisher, where alpha between M1 and M2 will never lead to a difference of delta between C1 and C2. In 2008, Jiki and Yu introduced the impossible boomerang distinguisher, where here we have alpha, delta, and delta prime that cannot lead to alpha prime between M3 and M4. So the question that comes next is how to build such impossible distinguisher. We have a technique for impossible differential distinguisher, which is called the miss-in-the-middle approach, where the attacker will start from the top and from the bottom difference, propagate both of them with probability 1 to the middle of the cipher, and hope for a contradiction in the middle here for beta and gamma. Liu proposed to follow the same type of technique to build impossible boomerang distinguisher. And in this type, for this thing, we will have four differences, alpha, alpha prime, delta, delta prime. All of them will be propagated with probability 1 to the middle. And we hope that in the middle, we have four differences that cannot sum to 0. So this is the contradiction. In this paper, we wanted to explore the possibility to extend this construction, and in particular to have an inequality and an incompatibility in the middle, which is not based on an inequality, but that will be based on a boomerang incompatibility of either 1 or 2 rounds. Our second contribution is the detail of complexity estimate for impossible boomerang attack. So we will give lower bounds on time, data, and complexity, memory complexities. And finally, our last contribution is the application of these techniques to two types of ciphers. So first, skinny EE, and to the Simon family of block cipher. So in what follow, I will mostly talk about the first and the last contribution. So if you're interested in the complexity estimate, please refer to the article. So let's start with the case of a 1-1 contradiction for an SPN cipher. In this figure here, I have one middle round of SPN. Beta and beta prime are the difference that were propagated with probability 1 from the top. Gamma, gamma prime are the ones that were propagated with probability 1 from the bottom. And so the first thing we can do here is make the difference go through all the linear operation of the round function. And we obtain a relation at the level of the S-box layer. Now we know that we will have a contradiction for this if we can show that we have a contradiction for at least one of the small S-boxes. So this means that actually we can rewrite and rephrase the initial problem of a 1-1 contradiction as a smaller and simpler problem of finding for one of the small S-box an impossible boomerang. Put into equation, this corresponds to having this set here, which is actually empty. And this set and the cardinality of this set is what was called in a 2022 paper the GBCT for Generalized Boomerang Connectivity Table. So again, we can rephrase the initial problem as finding for one of the S-box differences so that the GBCT is actually equal to 0. So let's now look at the specific case where we have alpha, which is equal to alpha prime, and delta, which is equal to delta prime. If we follow the same reasoning as previously, we obtain this relation here that must be impossible. This corresponds to this set, and the cardinality of this set is actually what was called the Boomerang connectivity table coefficient at Eurocrypt 2018. What is interesting about this specific case is that it will be simpler to search for such a distinguisher for an automatic tool because we only have two different, the two trails at the top are the same, and the two trails at the bottom are also the same. Also, it will be simpler to search for a key recovery for this type of distinguisher, because actually when we will have some rounds here for the key recovery step at the top, we will have exactly the same key material on the left and on the right. And similarly, at the bottom, we will have the same key material in front and behind. So sometimes it will be simpler and even more efficient to do so. We can remark here that this specific case was not covered by loose framework, because in loose framework, we need to have an inequality in the middle here. So we need to have at least alpha, which is different from alpha prime, or delta that is different from delta prime. So we wanted to apply this specific case to a variant of Skinny that was proposed at Crypto 2022, which is called Skinny EE, and for which we have a master trick, which is 4 times the size of the block. So for this variant of Skinny, the trick key framework is not followed, but we will have actually a linear trick schedule and independently a key schedule. So we can also see here that the one trick will be added on the first 2 rows of the state, and the one key will be added at the bottom. Regarding the other parameter, we have a 64-bit block, a 128-bit key, and a 256-bit trick, and this run function is iterated 56 times. So we built an automatic tool to search for impossible boomerang distinguisher on this variant of Skinny in the related trick scenario. So the first thing is to look for the red and for the blue trail. So here we simply say that we have a difference that will be propagated with property 1. We next need to show that and to tell the model that we want a contradiction in the middle. So to do so, what we do is that we will tell the model that we want that for one S-box in the middle, we want that the input of this S-box is known and different from 0. Whereas for the same S-box, we want that the output difference is known and different from 0 in the bottom trail. So once we have this, we ask for a truncated solution to the model, and we will next instantiate the differences so that the BCT of our exact differences is actually equal to 0. So regarding the detail of our model, we base ourselves on the impossible differential model proposed at Eurocrypt 2023. We use Minizinc and we use the CP solver or tools. So here is the 21 related trick impossible boomerang distinguisher that we found on this variant of Skinny. So as we can see here, the solver put a lot of blank round at the top and at the bottom. And here the BCT contradiction was made possible from the fact that we have a trick schedule which is actually linear, which created the possibility to know all the green differences and together with the red differences in the lower trail. From this distinguisher, we were able to build a 29-round rated trick impossible boomerang attack on this variant of Skinny. And at the time of writing the article, it was scoring 2 more rounds than the best attack to date. So let's now look at the case of Feistel cipher. With the notation given in this figure here, we can write what it means for a boomerang to come back over 1 middle round of a Feistel cipher. And we obtain these 2 equations here. Now, if we want to show that there is a contradiction, we need to show that either the first or the second one is impossible. So actually, if we want to prove wrong the first equation, it actually corresponds to an inequality similar to what was proposed by Lou, because these 4 differences actually correspond to the differences in the left branch of the Feistel cipher. So this is easy to understand why we have this equation. This simply comes from the fact that in the Feistel round, we have half of the state, which is just swapped and copied. Now, if we want to show that the second equation is wrong, what we can say is that if F is based on an S-box layer, it will be equivalent to having a FBCT, which is, or a variant of the FBCT, that is actually equal to 0. However, not all Feistel are S-box based, so we wanted to study another type of cipher, and in particular here, the Simon family of block cipher. So we started by applying the two previous equations to the F function of Simon, which is recalled here, and we obtained these two equations here. What we can see is that the second equation actually depends on XL, which is the value on the left branch of the Feistel. So this is a problem because actually we would like to be able to conclude that we have a contradiction without the knowledge of XL, the value, but only from the knowledge of the differences that were propagated with 41. So what we propose to do here is to add the constraint that delta R is equal to delta prime R, that will actually cancel out the impact of XL. And we obtain this free equation here that we want to be satisfied for at least one of the bits in the middle round of Simon. So we use this free equation to build a first SMT model, and we apply it to the 10 version of Simon in various distinguishing scenarios. But we also proposed a second SMT model, which we call the unsat SMT model, and which works a bit differently. So for this model, we will actually just write the Simon encryption function in SMT, also include the differences of the boomerang, so alpha and delta, together with the difference in the key, if there's a difference in the key. And we will ask the model to find a quartet that is a solution to this specific configuration, so a quartet of messages and a quartet of key. And if the solver replies with unsat, it means that there's no solution and that we have an impossible boomerang in front of us. So this is quite a powerful technique, but actually this is a bit slow. And we were not able to find any new impossible boomerang distinguisher with this technique that was not already found with the previous technique. But actually, it could have captured any type of impossible boomerang distinguisher, even if the contradiction was a bit more complicated than the previous one. So with our distinguisher, we were able to build a 23-round related key impossible boomerang attack on Simon. And unfortunately, it was covering 2 less rounds than the best attack known to date. So before concluding, let's look at the possibility of having a 2-round contradiction for an SPN cipher. So as previously, the first thing we can do is make the difference go through all the linear operation of the round function, and we obtain this relation here. Now, to conclude from this, what we can do is, assuming that the middle key is random, considering all the possible intermediate differences, and show an impossibility for absolutely all of them. More into details, it corresponds to going over all the possibility for B, B prime, and G prime, the differences here. Okay. Compute the number of solutions for each of the S boxes as we have, so both in the first and in the second S box layer. And we put everything together with this big formula. We will be able to show that we have an incompatibility if none of this solution is possible. So we can use this technique, but actually this is quite computationally expensive to do so. So this formula here is really similar to a notion that was introduced in 2021, which is the so-called double boomerang connectivity table, or DBCT. However, there is a big difference between the two that come from the sum here that is done. And actually, we can see that for the DBCT, we only take into account quartet with equal differences in facing sides in the middle of the boomerang. So this corresponds to this BE and BE here that are exactly the same, and the same for G and G. Whereas previously, for taking everything into account, we can also have B and B prime that are potentially different, and the same for G and G prime. So this means that some possibilities of configuration in the middle are totally left out, and this implies that having a DBCT coefficient which is 0 in the middle is actually insufficient to claim an impossibility. Unfortunately, this difference was missed by the author of this paper, which is the paper that was presented just before, and we were able to find a counterexample of a returning quartet over 2 middle rounds of what they propose, for which there is a DBCT which is equal to 0, but that is actually a returning quartet. So the suitable table to use in this case is the DBCT star or the GDBCT, for which all the middle differences will be taken into account. So it's time to conclude. So impossible boomerang distinguisher have several advantages over other technique. When compared to boomerang distinguisher, we can say that at least their exact probability is easier to capture correctly. Also, when we compare them with the impossible differential distinguisher, we can see that since we have more freedom in the trick and in the key differences, we might be able to cover more rounds in the distinguisher. And finally, as we show in this talk, there are various construction techniques. So either the unsat model or the 0, 1, or 2-run incompatibility. But in the case of a 2-run incompatibility, please be careful about which table you're using. Thank you for your attention.
Thanks for the talk. Do you have any questions? I see questions.
Thank you. Thank you. Could you go back to slide 13? So you say you've on the unsat SMT model, you fix the difference in the keys.
Yes.
Or above that, you fix input and output state differences of the boomerang distinguisher. How do you get these differences to begin with?
It's mostly intuition. So here, so it's a bit of intuition and also testing things that it's mostly intuition, I would say. So we try a lot of differences with 1-bit differences. And when we add the key differences, we will choose this difference in the key so that it cancels out with the state differences. So yeah, this is what we believe will cover them.
So you don't have an automatic approach to find good differences there?
No.
Thanks.
There was maybe another question, the last one.
Thank you, Virginie, for the very nice talk. My question is also regarding this slide. For the unsat model, it means you model the circuit 4 times, right?
Yeah.
And I wanted to know what if we modeled kind of 2 times? I mean, the difference, the propagation of difference in forward and backward but not with probability 1, just normally, right? It will be 2 models propagating difference forward and backward through the entire distinguishers.
So you mean in the unsat model?
The unsat model, yeah.
So in the unsat model, if this is not propagation of difference, this is just
I see.
encryption.
Yeah, that's I wanted to confirm with you. This is modeling the circuit 4 times, right?
Yes.
4 times, and then you fix the difference. But I'm talking about another approach. Let's say, what if we model the propagation of difference in a set of values? The difference, the propagation of difference forward and backward, just normally, and fix input-output difference. But what it has, like what the extra thing it has compared to the normal model, what if we put the constraints for each BCT for all the boxes? Does it capture all of the contradictions? Did you get my point?
Yeah, but I think if you only model the difference, you might skip other type of incompatibility. Like for instance, incompatibility that comes from the key schedule or relation between the key that are captured by this model and that might not be captured by other type of models.
Thanks.
Thank you.
Okay. So let's thank Virginie and all the speakers of the session again.